Section 5.2 looks at what are called extreme values, relative and absolute extrema. Now, first of all, let's talk about relative. So, relative extrema. Suppose you had a function. I'll just draw a picture for you of a graph. Suppose you had a function, that looks something like this. So here's a function f of x. The word extreme refers to extreme values of the function. Basically what it means is what we call max-min values, the maximum value of the function and the minimum value of the function. If I said to you, what's the largest value on this function? I'm referring to the y values. What's the highest point on the graph? Well, obviously this graph just keeps going to infinity, and so your answer would just be, well, the highest value is infinity and the lowest is negative infinity. The term relative means just in a localized area. So if you look at this graph, even though it just goes off to infinity, if you just concentrate on this region right here where there's a bump, this point right here, let's say we called that point C, comma, F at C. So I'm just referring to the x value as C. You'll see why in a second why I want to call it C. And then, of course, the y value would just be the function at C. This point right here, even though it isn't the highest point in total on the graph, right in this localized region right here, it is the highest point. So we call this point right here either, some people use the word relative, some people use the word local. This point that I indicated is called a local maximum value. The word local is just another term. Some people would use the term relative. Your textbook uses them interchanges the word. So it's either a local max value or a relative max value. So the word relative or local doesn't mean the overall graph. It just means in that region the graph seems to have a highest point. Same with this point right here, where the graph seems to reach a bit of a valley, that would be called a local minimum value. So this point right here, this would be a local minimum value. Now you'll notice that those 2 points that I've indicated on the graph, in terms of calculus, there's something very significant about those points. Remember that a derivative is the slope of a tangent line. Well, when this curve reaches its peak and starts to come back down, the tangents would be positive, and then they would flatten out and it would become 0 right here, and then it would start to decrease and become negative. So if you actually do a tangent right at this point, what's significant about that is that the tangent line would have a slope of 0. In other words, the derivative would have a slope of 0. The same thing for this minimum value. This local minimum value seems to have a derivative of 0. So we seem to be onto something there. If you wanted to find local or relative extrema, then maybe we should look for places where the derivative is 0. But there's one other situation where that could happen. What if the graph, instead of being a nice, smooth, concave down graph like that, what if it had come up like this? What if it had, we call this a cusp. What if the graph had done something like that? Suppose that was our function f of x. Now this point right here, once again, would be a max value. In this case, it happens to be also the very highest point on the graph, but this graph could have turned around and come back up like this. So this point right here is a local max value, but at this point, the derivative is not 0. In fact, what's happening here is the derivatives, the slopes are getting steeper and steeper and steeper, and right at this point right here, the slope would actually be undefined. It would be vertical. And so what I'm trying to show you in these two pictures is that if we're looking for relative extrema, either max or min values, then the two places we need to look are any point C where the derivative is either 0 or where the derivative doesn't exist, where it's undefined. So we call these critical numbers, and that's why I use the letter C. So a critical number so the term critical number. A critical number, we say that a function f of x has a little trouble spelling there. We say that a function f of x has a critical number at x equals c if f prime, the derivative at c, is 0, or f prime at c does not exist, but now a really important condition here, and x equals c is in the domain of f of x. And the reason for that condition about being in the domain is the graph may have an asymptote. If a graph has an asymptote at some point x equals c, then obviously the derivative would not exist, but it wouldn't be a local max or a local min. And so if you had a picture of a graph that, let's say, looked like this, let's say you had a function where there was an asymptote, let's say right here, at some point x equals c. Well, at that point x equals c, the derivative would not exist. F prime at c would not exist because you can't plug the number c into the derivative because the function doesn't exist there. We would not call that a local extrema or a relative extrema because it just doesn't exist. So when you're looking for critical numbers will either be where the derivative is 0, you'll have a horizontal tangent, or any place where the derivative doesn't exist, but the point itself does exist on the graph. So the point C has to be in the domain. So this is a very important condition. So now what we'll do is we'll do some examples, and I'll show you how we can actually find the critical numbers of a function. So in this first example, we have the function f of x equals x squared plus 4x minus 11. I picked this as our first example because you may recognize the graph. It's a quadratic function. And so if you just ask it, you might want to ask yourself the question, well, how many critical numbers would you expect? If you think about the picture of a quadratic function, it's a parabola. How many places does it reach a local max or local min? So let's go about finding the critical numbers. So critical numbers will occur for any value c where the derivative is 0 or the derivative doesn't exist. Well, in the case of a polynomial function, if we take the derivative f prime, we also get a polynomial. We get 2x plus 4. Polynomial functions are defined for every value, so there's no problem here with the derivative never existing. The domain of this function is all real numbers. So all we have to worry about is where it would be 0. So what you do is you take your derivative and you just make it equal to 0. You turn it into an equation. So one of the skills you're going to have to develop now and become good at is not only taking a derivative, but once you've got the derivative, you're often going to now be asked to solve an equation. In this case, the equation is pretty simple. It's linear, so we would just move the 4 over and divide by 2. So we're going to get x equals minus 2. X equals minus 2 is called a critical number. What that means is, at that point, x equals minus 2, we're probably going to have a relative extrema. Now, I picked this example because we know what's happening. If you graph a parabola, what this means is if you went over to negative 2, at this point the tangent is horizontal. Now, if you wanted to find the y value, you'd have to take your function f and plug negative 2 in. So if we did that, we'd get negative 2 squared, which is 4. 4, take away 8, take away 11. So we'd end up with 4, take away 19, or minus 15. So at negative 2, if you went down here to minus 15, we know that at that point right there, our tangent is horizontal. So we have a relative extrema. Without doing other investigating, we really don't know at this point whether it's a relative max or relative min unless you just understand the graph. In this case, it's a parabola concave up. So we do know that the graph looks something like this. We do know it's a concave up parabola, and so what we've just located is its vertex. So you can immediately see the applications for graphing. If you wanted to graph this function fairly accurately, it'd be nice to know where it had a turning point. or a relative extrema. And in the case of a more complicated function, like a cubic or a quartic, where there's going to be multiple bumps, obviously finding critical numbers is going to give us a pretty good indication of what the graph looks like. And again, that's the focus of Chapter 5, graphical applications of the derivative. Now in that case, finding the critical numbers, in the case of polynomials, finding critical numbers is pretty simple. But what if you had a function that was a little more complicated? What if you had the function f of x equals x squared over x minus 2? And we wanted to find the critical numbers. Now the first thing we should probably realize right now is that the critical numbers here, critical numbers only exist if the value of c is in the domain of the function. So immediately you'll notice we have a restriction. The restriction is that x cannot equal 2. At x equals 2, there's going to be a vertical asymptote. So regardless of what comes out of our work here, x equals 2 cannot ever be a critical number because it's a restriction on our domain. So to find the critical number, we look for any place where the derivative is 0 or the derivative doesn't exist. Either way, we got to take the derivative. So we take the derivative f prime using the quotient rule. So 2x times x minus 2 subtract 1 times x squared all over x minus 2 squared. You take your derivative and now you look for two things. You look for any place where the derivative doesn't exist or any place where the derivative is equal to 0. Well, you'll notice that the derivative doesn't exist at the value of 2. If you were to put 2 into this derivative, if we were to go f prime at 2, what would happen is we would get some number on top, which I guess in this case it would be 4. We get minus 4. But what would happen is on the bottom we'd get 0. So you might think, okay, the derivative doesn't exist here, therefore I have a critical point. But remember that the critical point has to be in the domain of the function. In this case, it's not in the domain, so 2 is not a critical point. Therefore, we're going to turn our attention to where the derivative is 0. So what you do is you make your derivative equal to 0. But now that you've made your derivative equal to 0, you have to be able to solve. At this point, I think something we talked about earlier, but it's worth repeating. Whenever you have a fraction equal to 0, you can ignore the denominator. The only way a fraction can be 0 is if the numerator is 0. So at this point, you can ignore the denominator. And so what you have now is just an equation where the numerator is equal to 0. Now, you can solve this one of two ways. You can take out your common factors if it's quite complicated. In this case, it's fairly simple. So what you might want to do here is just distribute. You might want to go 2x squared minus 4x minus x squared equals 0. 2x squared minus x squared is just x squared minus 4x equals 0. Take out your common factor of x, which, by the way, we could have done at the beginning, and you'll get x minus 4 equals 0. And you'll notice that we're going to get two answers. We're going to get that there's a derivative that's equal to 0 at x equals 0 and at x equals 4. Okay, so we have two critical numbers. Critical numbers being any values of x where the derivative is equal to 0 or any values of x where the derivative does not exist. We can't count this value of x because it's not in the domain, so our two critical points would be at x equals 0 or at x equals 4. I'd like to do one final example of critical numbers. In this case, the function is f of x equals the square root of x. So again, first of all, let's identify our domain. We can't take the square root of a negative number, but we can take the square root of 0 or anything positive. So in this case, our domain is that x is greater than or equal to 0, or using interval notation, our domain would be 0 to infinity. And the question's asking for critical numbers. So we take the derivative, f prime. Now recall, if you want to take the derivative of a root, you have to change it to an exponent. So this would be x to the 1/2. So the derivative would be 1/2 x to the minus 1/2 which would be 1 over 2 root x. Now, the critical number can occur at one of two places, either where the derivative does not exist or where the derivative is 0. A derivative will not exist if you divide by 0. Notice that if we actually plug x equals 0 into this function, the derivative will not exist. Yet 0 is part of the domain. So x equals 0 would be a critical number. It means that at that point, the tangent doesn't exist. I don't know if you know what that graph looks like, but if you graph the square root of x, the square root of x would just look something like that. And what's happening is right here at 0, the tangent is actually vertical. So that would be called a critical point or critical number, but the tangent is not horizontal. The tangent or the derivative does not exist. The only other place a critical number can occur is where the derivative is 0. But if you make this equal to 0, 1 over 2 root x equals 0, there's no solution. The only way a fraction can be 0 is if the numerator is 0. You can cross off the denominator. Well, we get 1 equals 0. There are no x's in the numerator. So there's no critical numbers there. So the only critical number in this case is 0. So far we've looked at what are called relative extrema. The next thing we want to turn our attention to are what are called absolute extrema, or sometimes they're referred to as global extrema. And the first thing I want to draw your attention to is what's called the extreme value theorem, which is really just common sense. It says that if you have a function f of x, and that function is continuous on some closed interval a to b, then the function has to have both a global maximum and a global minimum. Global refers to the absolute, the biggest value possible. I'd like to just draw a few pictures for you and show you what I mean by that, some of the things that can happen. So let's say we had a function, and there was some point x equals a, and some point x equals b. And we were drawing a graph between a and b. So what are different things that could happen? Well, I'll just show you with some examples. So let's say those were the points a and b. What the graph might do is the graph might just be a nice, smooth, continuous graph joining those points a and b. So nowhere on that interval are there any critical values. There's no place where the derivative is 0. There's no place where the derivative doesn't exist. But the curve does have a highest point and a lowest point. That's really all absolute extrema means, is that on some interval between a and b, every graph has to have a highest point and a lowest point. In this case, the lowest point and the highest point would just be where the function begins and where it ends. These are called absolute extrema or global extrema. Another thing that could happen, so again, and you understand that these points a and b are just arbitrary. They could be anywhere, any x values. What if the graph started here and finished here? But what if the graph went up like this, turned around, and came back down? Now if I said to you, what's the absolute highest point on the graph and what's the absolute lowest point? Well, the absolute lowest point, the minimum, the global minimum, would be where it started at x equals a. But the absolute highest would not be this endpoint. It would be up here. And again, the significance of that point is if you drew a tangent, the tangent would be horizontal. So I think you can see maybe where we're going with this. If you want to find the absolute extrema of a function over some closed interval, your choices are maybe where it begins and where it ends, or somewhere in between where there's a critical point. So another one might be something like x equals a, x equals b, and again, starting here, finishing here. But you can see that now the graph might come up like this, come back down, and come back up. In which case, our absolute or global extrema are going to be the points up here, where the derivative is 0, and the points down here where the point down here where the derivative is 0. So if you're looking for the absolute or global extrema of a function over some closed interval, you're either going to look at the beginning and the end points of the interval, or somewhere in between where there's a critical point. These critical points could also have been cusps. They could have been where the derivative doesn't exist. The graph might have come up like this and come back down like that. So it didn't have to be a derivative of 0, it just had to be a critical point. Remember that the critical point could be one of two different situations. So then, just to summarize, if you're looking for the absolute extrema or global extrema on a function over a given interval, here are the steps you're going to follow. Number 1, find all the critical values of the function on that interval. So look for any place where the derivative is 0 or the derivative doesn't exist. Number 2, evaluate the function at these critical values. You're looking for the y values. The max and the min values are always the y values. So take your critical values you found and plug them into the function and get the y values. Then take your endpoints a and b and plug them into the function and find those y values. And then simply identify the largest and smallest values. The theory here is that if you're looking for the global extrema of a function over a given interval, that they can only occur at one of 2 points, one of 2 places, either at the endpoints or at any point in between where you have a critical value. So then all you do is take the y values, and the largest one will be the maximum and the smallest one will be the minimum. So we'll do a few examples and see how this actually works. So in our first example, the instruction would be find the absolute extrema. So what we're doing here is we're looking for the highest and the lowest point on the graph in the interval 1 to 4. So we're only interested in analyzing this graph between 1 and 4. So according to the steps that we just looked at, the absolute extrema can only occur in one of 2 places, at any critical value of x or the endpoints. Now it doesn't matter which order you wish to do these in. I'll do the endpoints first. So what I would do here is I would take my function f and I would plug in 1. So we're not doing any calculus here, we're just evaluating a function. So I would get 1, take away 4, so minus 3, take away 1, minus 4. If I was to plug in 4, I would get 4 squared, which is 16. 16 minus 16 is 0, take away 1. Now I would find all my critical values, my critical numbers, so f prime of x equals 2x minus 4. I'm looking for any place where the derivative doesn't exist or is equal to 0. In the case of a polynomial, it's just where it's equal to 0. So I get x equals 2. Now x equals 2 happens to be in my interval. It can often be that this point would not be in your interval, in which case it would be of no interest to you. But it is in our interval, so I take that value 2 and I plug it into my function. And I get 2 squared is 4. 4 take away 8 is minus 4. Minus 4 take away 1 is minus 5. Once you've done that, you're looking for the absolute extrema. You're looking for the highest and the lowest point on the graph. So the highest point would be the biggest y value. So this negative 1. So negative 1 is a global maximum value, and the number negative 5 is a global minimum value. So we've just identified, if you were to draw a picture of this graph between 1 and 4, we've just identified the absolute highest point on the graph and the absolute lowest point on the graph. Another example might be f of x equals x plus 1 squared over x minus 1 on the interval 2, 4. So we're looking for, once again, the absolute extrema. So we take our endpoints, so we plug in 2 into our function, and we would get 2 plus 1. 3 squared is 9 over 1. So this would be 9. Plug in our other endpoint 4, and we would get 4 plus 1, which is 5 squared is 25. 25 over 3. which if you want would be 8 1/3. Now we have to look for critical values. When you're looking for critical values, always be aware of numbers that aren't in the domain. In this case, the number 1 is not in the domain, so we can't ever have a critical value at 1, which doesn't matter to us anyway because 1 is not inside of our interval. So we take the derivative f prime, which would be 2 times x plus 1 times the derivative of the inside, which would just be 1, times the bottom, minus the derivative of the bottom, which is 1, times the top, all over the denominator squared. We're interested in where that's equal to 0. The only place it's undefined would be at 1, and 1 is not in the domain anyway, so it's not a critical number. Now to solve this, I would take out a common factor. I would take out an x plus 1 as a common factor. That would leave me with 2 times x minus 1, so 2x minus 2, minus, and I still have one of these left over, x plus 1. So I'm subtracting x plus 1, so subtract x, subtract 1, equals 0. I can disregard the denominator. At this point, your derivative itself has a denominator, but when you solve this equal to 0, you can just ignore the denominator. So I have x plus 1 times 2x minus x is x minus 3. So it turns out that I have critical numbers at -1 and 3. Now -1, what that means is that this graph has a horizontal tangent at -1, which would be a relative extrema. But we're only interested in analyzing this graph between 2 and 4. So we would just disregard the -1, but 3 is of interest to us. So we have to plug 3 into our function, which would give us 3 plus 1 is 4 squared is 16. 16 over 2 is 8. So now we can answer the question. We would say that the absolute or global max is the biggest number. So 9 is a global max. And the number 8 is the smallest number, so 8 is a global min.